Welcome. This question says, show that a 3 cubic meter sphere that has a density of 12 kilograms per cubic meter has an apparent weight of 120 newtons when it is submerged in a fluid that has a density of 8 kilograms per cubic meter. So here's my experimental setup, and I have a beam at the top that's holding two force gauges. This is like a spring balance, and when I just hold the spring balance to read the weight of the mass, I'll get one weight. But then if I just leave that system where it is but jack up a beaker of fluid so that it surrounds the sphere, I'll find I get a lower reading of weight, and that's called the apparent weight. So I'm looking for the value of this apparent weight when the sphere in this case is surrounded by fluid. Clearly the weight stays the weight. The weight is the same in both cases. The difference is the fact in this case we have a significant buoyant force. So we're going to say, well, let's visualize the case with the apparent weight. So here we have our sphere. And we do have a weight, so let's just call it Fg. And we do have a buoyant force, so let's call that Fb. Those two are not equal. Clearly, if they were, the object would float. And the implication is that this object is not floating. So let me actually do this a little bit better. Let's make sure that we recognize that the weight is bigger than the buoyant force. And so what's keeping this in equilibrium is the upward pull of this force gauge, and this is the apparent weight. So we have a second force pointing upwards, and we'll call this FAW. So we have our buoyant force caused by the liquid, we have our weight, which is the inherent pull of the Earth on the mass of the sphere material. And what's causing the equilibrium is the force gauge, and the force gauge is pulling up with the apparent weight. And we want to calculate this. It's an equilibrium, it's not accelerating upwards or downwards, so if we think back about our standard mechanics physics, we say that the sum of the forces vertical is equal to 0. And the sum of the forces vertical is equal to, looking at my diagram, I have a plus apparent weight, I have a plus buoyant force, and I add on to that a minus weight of the actual object. How do I work these things out? Oh, and I'm sorry, I didn't finish that off. And those added together must equal 0 because there's no acceleration vertically. So then I can say, okay, my apparent weight is going to equal my Fg minus my Fb. And so my apparent weight is equal to, well, the force of gravity, the weight of this, is going to be the density of the object times g times the volume of the object. And then for our buoyant force, well, the buoyant force is all about the fluid, so it's the density of the fluid times g times the volume of the displaced fluid. And what we see here is that when the thing is submerged, the volume of the displaced fluid is the same as the volume of the object. So we can say our apparent weight is equal to the density of the object. Well, there's the density of the object, so that's 12. And g on the surface of the Earth is 10 newtons for every kilogram. And the volume of the object, it's a 3 cubic meter object, minus the density of the fluid. The density of the fluid is 8. And G is 10. And so this is the conceptual bit. The volume of the displaced fluid when it's completely submerged is the same as the volume of the object that is submerged. So that would also be 3. So my apparent weight is equal to 3 12s of 36, that's 360, minus 3 8s of 24, that's 240. So my apparent weight is equal to 36 minus 24, that's 120 newtons. That's 120 newtons, and that's what we were supposed to show. So let's recognize that in the absence of this buoyant fluid, then the weight of the object would be simply, it would be its density, which is 12, times its g, which is 10, times its volume, which is 3, which would be 360 newtons. But simply because we surround it by a fluid of density 8 kilograms per cubic meter, the reading on our force gauge is reduced to 120 newtons, and that is the apparent weight. And there we have it.